This webinar has been part of a series. There's one more after today on July 7th. We hope you've been able to join us for the other sessions. Recordings of each of the previous sessions and additional resources will be posted online at the mdcleanenergy.org website. Webinar attendees can receive one continuing forestry education credit from the Society of American Foresters for each session that they attend. Other credential holders may also be able to self-report this series to meet continuing education requirements. At the end of today's session, Zoom will open a survey page in attendee browsers. After leaving the webinar, please submit the form to ensure that we have your correct information for CE credit reporting and verification. If you need assistance reporting CE education hours, please email info@mdcleanenergy.org. We want to thank our partners who have organized this series as part of the Spurring Fossil-Free Biomass Initiative funded by the Maryland Agriculture, Education, and Rural Development Assistance Fund. The partners are, you'll see their logos below, including the Maryland Forestry Foundation, Maryland Clean Energy Center, the Maryland Department of Natural Resources, and the Sustainable Forestry Council. So we'll get started today. At the end of the program, we'll have time for Q&A. Please remember that questions for the panelists can be submitted via the Q&A feature at the bottom of your screen at any time during the presentation, and you can use the chat box if you need technical support. Using woody biomass for energy has neutral impacts on carbon emissions when the right policy and regulatory framework are in place. It's important for educated stakeholders to work together to create sound policies and regulations for the harvest and use of woody biomass energy. In this webinar, participants will gain a broader understanding of the readily available and affordable feedstock, as well as transportation, and whether or not that is a roadblock to adoption, right-size model systems for various applications. Are systems economically competitive, viable to install, and uncomplicated to operate? And how does the technology of related woody biomass energy systems meet or exceed Maryland air and water quality requirements for permitting? Our first presenter, Dan Wilson, is the Vice President for Wilson Engineering Services, PC. When I met all of the speakers, there are bios available online for you all to view. I'll tell you a little bit about Dan, but I asked each of them to share with me what their favorite tree was. It was interesting that some of these forestry experts struggled to pick a favorite tree. Dan's favorite tree is the willow tree. He has one on his farm, has had one on his farm. He said it was good for climbing and a great home for orioles. As I mentioned, Dan is Vice President at Wilson Engineering Services. Prior to founding WES in 2008, Dan was an engineering project manager at Gahagan and Bryan Associates, Inc. He's a registered professional engineer and holds a Bachelor's of Science in Agriculture and Biological Engineering from Penn State University and a Master of Civil Engineering from Johns Hopkins University. He's the current chairman of the Biomass Thermal Energy Council. Good morning, Dan.
Morning. Now, thanks very much for the opportunity to speak with you this morning, and see if we can get my presentation up here. I'm going to be discussing heating and cooling, so thermal energy and combined heat and power. Looks like I need permission to share the screen if that's possible. Okay, here we go. So I'm going to be talking about thermal energy and combined heat and power with wood energy. And specifically what I'm going to do is use project examples to highlight key design aspects of these types of projects. And before I get into the example projects, what I'd like to do is take a minute just to talk about, on a project basis, what the focus needs to be for these wind energy systems. So what we're trying to do is meet the needs of an end user with an individual project. So we need to get to the facility and really understand their heating, cooling, and electrical demands in detail We need to know how these energy demands vary over time, and then what the cost of energy is for supplying these demands. Once we know that in a lot of detail, then we can talk about what opportunities there might be for using wood energy. And there's a lot of great technologies that are available and very clean and efficient that are commercially available for the wood energy industry. And what these are able to do is convert that sun's energy that's stored in the solid wood form into heat, and then run it through different processes and machines so we can provide heat, cooling, and electricity to these facilities. So the focus needs to be first on the end user. And when you look at the end user, economics are a big picture item for them, and really one of the main concerns, obviously, at an individual facility. There's a lot of great benefits with wood energy systems, but we have to be able to show the owner an energy savings, or else we can't realize those environmental and social benefits that other webinar presenters have already talked about. When you look at the economics, the quick way to do that is to quickly look at the energy prices. So what's the cost of delivered energy from various fuels and technologies? I'm not going to go through this slide in detail, but this presents some that you would expect for a decent sized energy user in the mid-Atlantic region, including Maryland. What you see here is, we'll start with the wood chips bar. You can see the cost of delivered energy once you factor in the cost of the fuel and the efficiency of the boiler or conversion system. There, we're coming in at about $5 per million BTU. It's pretty typical for delivered energy from wood chips. And you can compare that to the other fuels on the chart. One thing that's interesting in Maryland is there is a thermal renewable energy credit, and that can have pretty significant value on the thermal energy side. So that's worth about $2.75 per million BTU right now, which is about 60% of the delivered cost of the wood chip energy. So that shows that there's some pretty interesting value there in Maryland that owners can possibly recoup. So now I'm going to get into specific project examples. And first, what I'm going to talk about are thermal energy only projects where we're only providing heating with a wood energy system. First project I'm going to talk about is a boarding school that was converted from an old monastery in New York. And this is about a $2.2 million project where the first thing that we had to do was convert the entire facility from steam over to hot water, and then convert the heating systems from 100% fossil fuels over to 100% wood energy. And with this project, I'm going to show some site pictures so you can see what this equipment looks like out in the field at a commercial scale. Here, what they did was they converted the existing coal bunker, which was under the parking lot, into the wood chip storage area. Once the chips are placed by the truck into the storage, they're not touched again by a person on site, by operation and maintenance staff. They're automatically delivered into the wood boiler system, which you see on the upper right here in the facility. Those provide heat, can transfer that heat to hot water, and then the hot water is stored in thermal storage tanks before being distributed out to the hydronic system that's in the facility itself. So I mentioned thermal storage tanks. That's one design aspect they want to talk a little bit about. So whenever you have a hot water system using wood energy, pretty much every time you're going to benefit from having a thermal storage tank as part of the integration to your facility. And what the tank does is it is literally just a big tank full of hot water, but it's plumbed in a certain way that allows it to store energy at a hotter temperature than is delivered out to the district system or to the building. And it decouples the demands in the facility from the load seen by the biomass or wood chip boiler. And that keeps the boiler from cycling, increases efficiency of the overall system, and also lets you meet peak loads above the capacity of the wood boiler itself for short periods of time, which can be very helpful for integration into your facility.
Yeah, I'm participating in a webinar.
The next project I want to talk about is another school in New Hampshire this time, and this is more of a campus setting. It's got 25 buildings across the campus, and there used to be a steam district heating system that was aging and needing replacement, and 19 boilers across the 25 buildings for this campus. They put in a new hot water district heating system, converting over from steam in a lot of cases, and then put in a new central plant to serve that new district energy system. A component of the central plant was a biomass energy system, and that provides significant value to the facility on an annual basis from energy savings, and then also from thermal renewable energy credits, which I'll talk about more here in a minute. In the end, on an annual basis, they're spending a net of about $60,000 a year to heat all the buildings at this facility in New Hampshire, which is a pretty good number. One of the items that I want to talk about, use this project to highlight, is the economics and how they use the biomass energy system and the value it provided to pay for deferred maintenance and a new heating infrastructure for the facility. Total project costs here are around $5 million, and the biomass portion of this project was about 17% of that. But that 17% expenditure provided enough savings to finance the entire project, plus provide some cash flow on an annual basis over and above what they were paying for the financing of the project. That's something that's pretty common approach that's used, and maybe something that could be used in Maryland. Another thing to discuss associated with this project is thermal RECs. In New Hampshire, their renewable portfolio standard incentivizes renewable thermal energy, and that's solar thermal, geothermal, and wood energy, to name a few of the available technologies that you can get funding for through this program. And essentially what you do is you meter the amount of renewable thermal energy provided to a facility, and 3.4 million BTUs, or a megawatt hour of heat, gets you one REC. Currently, the RECs are worth around $6 per million BTU in New Hampshire, which is pretty valuable when you consider that the cost of energy provided by the wood is around $4 to $5 per million BTU. Maryland actually has a thermal REC as well, and it includes biomass. One thing I'll say about Maryland's thermal REC is that the language is very, very confusing with respect to how it treats wood. And so I think that's something that needs to be clarified if folks are going to take advantage of it as an opportunity to push projects forward in Maryland. But it exists, and it's a tier 1 REC is what it generates, and that's worth right now around $2.75 per million BTU on a current market rate for the RECs. There's a lot of states out there that have thermal RECs in their mix with the PUC or the renewable portfolio standard, but they're not structured in a way to really have any substantive value. Maryland's are actually pretty valuable. Speaking of Maryland, I thought it might be helpful to just identify an example project for what might be able to be done in Maryland. This is a project that has been evaluated already for wood energy system. And this is at a Baltimore City school. And you can see the square there shows where the boiler room is at this facility. And interestingly, right across 83 on the other side there is one of the city's wood disposal facilities, where they sort waste wood from urban wood residues from tree trimmings and so forth. So they bring a lot of the city's waste there. So that's kind of convenient. Across the street, they have a boiler room that's big enough to put in a wood energy system that could cover 90% of the heating loads at this facility on an annual basis. To do that, you probably spend on the order of $2 to $2.5 million at the facility. You can see in some of these pictures just a very generic layout of what a wood energy system layout could look like in existing mechanical space, and a picture of the boiler room that exists now. If you spent the money on this project, it would probably save on the order of $270,000 a year on offsetting the use of fuel oil in this school. And with the RECs, they would provide around $45,000 a year. So if you look at the payback on that for a system that has 25 to 30 or possibly longer lifetime, that's a pretty good payback for something that provides all the benefits, environmental and social, that were discussed with the other webinars, and at a school that's going to be around a long time. So now that we've talked about some thermal systems, it's time to add power to the discussion. So this example is a thermally led biomass district energy system at a hospital in Wisconsin. And here they're able to serve about 1.1 million square feet across 2 facilities with a biomass energy system that covers 80% of their natural gas use at the facility and about 9% of their electric needs on an annual basis. I mentioned thermally led combined heat and power. What exactly does that mean? If you look at the process for generating power with biomass in particular, but other fuels as well, what you have to do is take the energy in the fuel, turn that into heat, and then use that to drive a machine, an engine, a turbine. And out of that machine, we're going to get a little bit of electricity, but we're mostly going to get heat. So what we do with thermally led, that means we're going to focus on designing the system around that heat portion and matching what it outputs to the needs of the facility. We're not wasting any energy. And the portion that's electricity, we're going to consider as a benefit of the project. That's kind of a bonus that we get for adding this machine into the mix. So if we view it that way, it's a very efficient and cost-effective way to generate power. This gives you the economics of a system similar to the one at the hospital that we identified here. The basic gist of this is that for around 1 to 3 cents per kilowatt hour, depending on the price of the wood that you're purchasing, a back pressure steam turbine can provide power for around that cost effectively. The other thing that's interesting with this is with the thermal RECs, since that is such a big portion of the energy cost, if you're using wood chips as your fuel, you can offset a lot of the cost of that power, so it's even less expensive than identified in the 1 to 3 cents per kilowatt hour. So we can't generate all a facility's needs. We can only generate what their thermal load dictates we can with this type of approach. But what we do generate is very cost effective and extremely efficient. Now let's add cooling to our examples. So here we have another hospital, and there they have a thermally led combined heat and power and district heating system. And this time we're going to discuss their thermal chillers, which are added to the mix. So this facility uses wood energy to cover 90% of their steam loads and approximately 90% on an annual basis of their cooling loads at the facility. They're also getting, through back pressure steam turbines, around 12% of their electric. If you look at thermal cooling and thermal chillers, these have been around for many decades, and it's a very mature technology. Really what dictates whether you can use it at your facility is if the economics make sense. What you have to have are pretty low cost heat or high cost electric or a mix of the two. And then also these are used very frequently at larger facilities, campuses, places where you're really concerned about resiliency and redundancy as another source for chilling. So you're not relying fully on the electric grid or the electric system at your facility with backup power. For cooling, you can also provide cooling in another way. So there are a lot of uses for these in design and ensuring you're redundant with systems. Usually economics are what dictate whether this makes sense for your facility. Just to give you an idea of what the economics look like here, the first 2 lines are absorption chiller machines with different thermal temperatures into them, and they show what the cost of per ton hour for cooling is if you're using a wood energy system. And then the next 2 are different approaches for using electric machines for cooling, and it shows the cost per ton hour. You can see that the wood systems are on par with or possibly save a little bit on the cost of cooling with the prices of wood and power we identified here. What can change this, again, pretty dramatically is the thermal REC, because that is such a substantial portion of like a wood chip delivered heat cost. We can get some pretty nice savings when you factor that in if we're looking at cooling with thermal chillers, especially at large facilities. So those are the projects. Now I want to run through some other key design aspects of projects generally. One of the keys is system sizing. I'm going to talk in detail about that in just a minute. I'm not going to get into storage and handling systems, but these are clearly key aspects of project design. One thing I would like to say about these is that it's really key that you have fuel flexibility with your energy system, your wood energy system. So there's always going to be a forest management in Maryland, as long as there's forest, which is hopefully for forever. And that means that industry, to manage the forest, is going to need an outlet for some kind of residue or waste material from the activities that they conduct in that management. What that is probably going to vary over time in terms of different types of forests as they evolve, or different products and markets from different industries have different residues from the forest products industry. But if you set yourself up to be flexible in your handling and conversion systems, that allows you to, over the next 20 to 40 years that you have your system, be sure that you're always able to get the lower cost material and to provide a benefit to take the residue that folks need to find a home for. I'm not going to spend a ton of time on it, but integration with facilities is also key. Fossil systems tend to cover up mistakes in design, or maybe less efficient designs for integration of fossil systems into a building. Wood energy systems tend to not cover up those mistakes as well. And so paying attention to that with the wood energy system is doubly important. And then also using vendors and installers with proven track records is really critical. So I'm going to spend a little bit of time about talking about sizing of systems and why that's important. The first thing and the most important step in any wood energy system evaluation is detailed load modeling. And until that's done, really not worth spending a ton of time on sizing systems. Really, you should focus your efforts on load modeling for the chillers, or for the cooling load, thermal load, and the electric load, and then you can get into sizing. Once you've done that, and here we're showing with this blue line a daily average steam demand for a campus. Once you have that load model done, you can size a system. One common approach to sizing a wood energy system is to select one unit that is going to cover 80 to 95% of the load. That means you're covering 80 to 95% of the savings, or capturing 85 to 90% of the savings with that one unit. So that's an efficient way economically to capture savings. And then for facilities where it makes sense from an economic perspective or redundancy perspective, you can add in 2 or 3 wood boilers in total to cover 100% of the load, or provide redundancy for the systems. In most cases, not all cases, but most cases, you will have a backup fossil fuel system that covers peaks, downtime, or low loads that the biomass energy system doesn't happen to cover. We do a fair amount of coming in after the fact to help troubleshoot systems, and I would say the number one, possibly number 2 issue that we run into with the wood energy systems, if there is a problem, is associated with the size of the unit. They turn down to about 25 to 30% of their rated capacity, a little lower at times, but typically you don't want to run them much below that. And so we find that systems that are much bigger than the loads that they're serving can have operational issues. And so a lot of times we'll go in and do a load model after the fact to compare that to what the installed capacity or design capacity for the system was, and identify items there. The other reason that it's really critical to focus on sizing is upfront cost and economics of the overall system. If you look at the upper left graph, you can see the installed boiler cost or size was maybe 4 times larger than it needed to be if our goal was to capture 90% of the thermal demand of the facility. So what that means is that we have not only the boiler is bigger, the building is bigger, the storage is bigger, the emission controls are bigger, all the pumps, the piping, everything costs more, and maybe not necessary. It might not be necessary to add that cost into the project if your goal really is to capture that 90% of the load and 90% of the savings. So that's the other reason that's really key to focus on sizing in an efficient way. I want to spend a little time talking about the quality of energy in buildings. And this isn't necessarily associated with wood energy systems, but is really critical to overall design, and then wood energy as well. So the basic idea that I'm trying to discuss here is, if you have a building that needs to be heated to 75 degrees, do you really need to send 300-degree steam out of your central plant, or even hotter, to that building so you can heat that air? The answer is you probably don't, and you can probably use 110-degree water or a lower temperature to provide that heating to your building. And a lot of times in the US, that's because our energy prices are typically pretty low, we haven't had to focus on that much. But as you look into trying to capture renewable energy, such as solar thermal or doing waste heat capture off of chillers or other systems that you happen to have at your facility, you find very quickly that those all get eliminated if you need to provide steam to the building. But if we could provide low temperature hot water to the building, we can start to pull heat from all kinds of interesting places that are either renewable or waste heat that's floating around our facility. So that applies to efficiency and renewable energy. It also applies to combined heat and power. We can get 4 times more power out of the same machine if we have if we had low temperature water in our building that we were trying to serve, as opposed to having steam in our building that we were trying to serve. We can do a lot better on the economics for CHP. Makes a huge difference there. District energy becomes a lot easier in terms of its efficiency for piping. And then on the wood side, in addition to the CHP benefits, flue gas condensation is a really great technology where we can condense all the steam and latent energy that's in the flue gas and capture that heat and use it in the building if we have a low temperature sink for our building, as opposed to needing, say, steam in the building. We can get up to 92% efficiency on the wood boiler pretty easily if we have a use for that heat. And it also helps us a little bit with emissions as well. One thing that's also important to talk about from the design side for wood energy is air quality. One thing we would recommend on every project that's done of any scale at all really is air quality modeling to inform your design. And even if you don't need it from a permitting, even if it's not required for permitting, air quality modeling is just a good design practice. It's not just for wood either, for any kind of fossil system with combustion. If you pay attention to the stack, any of these systems can provide very, very minimal impacts on air quality, and you can design them to ensure that even under the absolute worst case conditions that probably will never occur, that you're not going to ever exceed national ambient air quality standards with your facility. And so it's really important to pay attention to that on the design side. An interesting thing from the Holderness project, the modeling for that project was done by the state of New Hampshire. That's a service they provide if you pay them. And they were able to identify that the wood energy system as designed actually improved air quality at that facility pretty dramatically, because attention was paid to location of the stack, stack design, and emission control design, as opposed to the fossil systems, which were old and didn't have any attention paid to that for them when they were installed. The final thing I'm going to discuss is decarbonizing thermal energy in the US or in Maryland. If you look at the total energy picture, 30 to 40% of the energy used in the US and Maryland's pretty similar is for thermal energy. And yet not a lot of policy to this point has been directed at that. And it's pretty hard to tackle your carbon goals as a society if you're ignoring 30 to 40% of your energy. So decarbonizing the thermal energy is really starting to be paid attention to by states and institutions. And at the state level, things like thermal recs that incentivize solar thermal, geothermal, wood energy, thermal energy sources that are renewable are really starting to become more prevalent. And then a lot of colleges and universities, for instance, are implementing technologies that are looking at renewable thermal for their district energy systems. They have a lot of carbon emissions associated with buildings, heating and cooling. And wood energy is a pretty good option for them, especially if they have district energy systems. We've seen a lot of that implemented. The other one that's pretty interesting is industrial steam users. A lot of the larger companies now are really paying attention to carbon emissions and trying to decarbonize their thermal energy. There's not a lot of options for them when you're talking about high temperature systems. Solar thermal doesn't do so well providing steam. And so I think that's probably an opportunity for biomass energy systems and wood energy in general, is to really help those types of folks in decarbonize their thermal energy systems for large energy users. One thing that's interesting is to look at when you're looking at greenhouse gas emissions is what's the cost to abate these emissions or to reduce greenhouse gases. Harvard has a really nice study that was done a couple years ago that shows what the cost is to reduce greenhouse gas emissions for various technologies across the globe and what the scale is there. You can see that at the lower right. The axis there shows that a negative cost for carbon offsets, that's a project that's going to save money and also achieve that goal. Projects that are positive mean we have to pay extra money to achieve that goal. So the best projects are options that are going to pay for themselves over their useful lives while achieving the greenhouse gas emissions. We didn't see in that study any identification of biomass thermal or combined heat and power as options there. So we thought it'd be interesting for projects that were implemented that we worked on, we thought it'd be interesting to identify what those looked like, that same metric looked like for those. And you can see that on the graph on the left. So while biomass thermal systems and CHP systems tend to cost a lot up front, they have very long useful lives, and their cost savings are very stable because they're using a waste material or a residue from forest management or industry. And that allows them to provide some pretty negative abatement costs, which is a pretty interesting way to look at these projects. Just to further emphasize that, this is from the Holderness school project that we talked about before. That project clearly paid for itself. And so what do the carbon emissions look like for that? So here are the net scope 1 emissions from the facility, from their heating system over time. The blue line is the monthly purchases of heating fuel in million BTUs. So included in there are things like oil, propane, and wood in the blue line. And you can see as soon as they started their wood boiler operation, they were able to reduce their red line, which is the net CO2 emissions in metric tons per month, to just a fraction of what it was previously. And so you can see how it's that project for that specific facility really decarbonizes a big chunk of their emissions at their facility, which are associated with the building heating systems. So that's the end of the presentation. I'd be happy to take any questions either now or later or off the call. So what I went over was thermal energy, so heating and cooling and combined heat and power, and these types of systems using wood energy. I think the message that I'd like you to take away is that in Maryland there are, because there is this residue material, it's not fair to call it a waste because you can do things with it, but it's a waste material out of industry that needs a home and out of forest management. And Maryland has some opportunities to decarbonize their thermal delivery systems for all kinds of different facilities using this waste material. And it's not going to work for every facility, but there is going to be a lot of facilities in Maryland that have the economics to make this make sense over time. So I appreciate you taking the time to let me speak to you and paying attention, and I'm looking forward to the rest of the presenters' talks.
Thank you, Dan. I think your point about decarbonizing thermal energy and that 30 to 40% of the energy used is for thermal energy is really important for us to consider when you think about woody biomass and the carbon capture that trees provide in combination with that. There's a real opportunity here. Our next presenter is Lou McCreery. Lou is the acting director of the Forest Service Wood Education and Resource Center and the Regional Innovations for the U.S. Forest Service Eastern Region. Lou focuses on maintaining a strong and vibrant hardwood industry throughout the 35-state Eastern hardwood region. He oversees efforts to increase the use of wood for energy and value-added projects across the 20-state area. He manages the Wood Energy Technical Assistance Team that provides hands-on assistance to building owners interested in using wood energy in their facility, and his team has helped more than 100 building owners implement wood energy at their facilities. Lou's favorite tree is the red spruce because he says it can exist for 50 years in the understory, but when released, it grows like a teenager and is prolific throughout the East Coast region from Maine to Florida. Welcome, Lou.
Thank you very much. It's a pleasure to be with folks today here, and I'd like to thank the folks at the Maryland Clean Energy Center for inviting me to participate. I'm going to talk a little bit about wood energy systems in commercial and industrial settings, and get into a little bit of the, maybe into the weeds on a couple of things, a couple of different technologies that we want to make sure folks consider when they are implementing projects. Also, I'd like to thank Dan Wilson. He's our partner. His firm is our partner in our wood energy technical assistance team, where we try to help facility owners take a look at wood and how wood can be used in their specific facility. And we believe in both being technology and vendor neutral. So we're really, we want to encourage the use of wood in whatever form it is, whether it's cordwood, pellets, or wood chips. We believe that wood energy systems can be efficient, clean, and automated, whether it's firewood, pellets, or wood chips. And now we have a couple of different type of wood chip systems that are being implemented around our region, both green wood chips and semi-dry product. The projects that we look at are across a wide variety of situations, but I think in all cases, they're really driven by savings. Cordwood systems, where they're utilized, can be lower cost, but certainly it requires more labor, and fuel management is very important. Wood chip projects, we find are higher capital cost, probably. In most cases, those are larger systems. The fuel costs are probably the lowest. And with the new semi-dry chips, they have a reduced capital cost to some extent because a number of larger pellet boilers are able to use semi-dry chips when their moisture content's below about 40%. And that means both the delivery systems, the storage systems, and the handling systems, as well as the boiler systems, are a bit less costly than the green chip version. While pellets are normally the highest cost wood fuel, many projects have much lower capital costs because of the equipment that's being used, whether it's storage, fuel delivery, or the combustion units. Cordwood systems, we've worked with a number of folks that are using cordwood in a commercial application and find it very effective. Harvard Forest, a facility in Massachusetts, eats about 45,000 square feet of space, office space and garage space, with a cordwood fired wood energy system. When using cordwood, it is really a requirement that you use the thermal storage technology that Dan Wilson mentioned earlier. Pellets, very automated systems, very little interaction required by the facility folks in using wood pellet systems. And wood chip systems, usually in larger commercial or industrial applications, they have a larger footprint, higher cost, but and a bit more interaction with the system than with a pellet system, but Automation is also significant in those systems. As Dan mentioned earlier, not a lot of interaction once the wood chips are put into the storage system. When we're working on projects, we certainly want to maximize the economic benefits to the owner, and that comes through really working on all of these particular system components, making sure that we have as much load as we can capture at the site, trying to identify if combined heat and power is an opportunity. As Dan mentioned, sizing is hugely important in the use of wood energy systems. Sizing of the thermal storage is also important. With any time you use a hydronic system or you have a hydronic energy delivery system, you want to be able to use thermal storage. You want to set up your system so that you maximize fuel flexibility. Make sure that you can handle the lowest cost fuel that may be in the region, the lowest quality fuel that may be in the region. And as Dan mentioned, we really want to focus on emissions and make sure the correct emissions control system is put in place. This is just an illustration of those key project components and highlighting again, you can actually use a steam system, generate steam, convert that steam to hot water heat all in one system, so that you can get the advantages or potential advantages of back pressure steam turbine, and also the advantages of using thermal storage and delivering heat to your system. And we really want to focus and point you to the use of thermal storage. It's a wonderful technology, widely used in Europe in their wood energy systems, and finally being more and more widely used in wood energy systems here in the United States. And can't say enough about the benefits, as Dan pointed out, to the use of thermal storage. This little diagram here is the key to a thermal storage system. As Dan mentioned, you're storing water at a much higher temperature than your building needs. And this little mixing valve that sits in between the thermal storage unit and your building is the key to maximizing the benefit of thermal storage. And it's a really elegant, simple system once folks understand how to use it. As far as emission controls go, we really encourage the use of ESPs, the electrostatic precipitators. They are efficient, and when you look at the costs, the maintenance costs over time, I think they do a much, you'll find them more cost effective than bag houses for the pollutants that are emitted from a clean wood system. Multi-clones are available and they work. The one concern we have about using multi-clones is you got to be careful about how they perform at lower output levels of your system. Usually they're geared to perform the best at high output levels, and to some extent some of their performance curves drop off as the system's output drops off. One of the things that Dan mentioned that I really want to focus on is flue gas condensation. This is a graphic of one type of flue gas condensation system. As he mentioned, the purpose is to harvest energy from the flue gas by utilizing the moisture that's in a moist fuel like green wood chips or even semi-dry wood chips. The neat thing about it, it is a technology that makes your system more efficient. At the same time, it has an impact on reducing emissions. It targets the condensable fraction of the pollution stream in the flue gas, and those are the items that normally end up being in the once they exit the stack and condense into small particles that are predominantly below 2.5 microns. The one thing that Dan mentioned is that we need a low temperature load to get the maximum benefit from this flue gas condensation system. And if you have a demand or can utilize that 100-degree hot water, either for preheating process water or for building heat with low temperature emitting systems, you can gain some significant advantages in your system efficiency. And I want to talk a little bit about where we see some of those advantages. Here's a graphic that takes a look at the unit energy cost for steam. The first bar is natural gas at $7.50 a million BTUs, and the energy cost of steam is about $9.79 per million BTUs. The next two bars are wood without flue gas condensation. That energy cost is about $3.86 a million BTUs. But if you use flue gas condensation, you drop the cost of that wood to, or that steam to about $2.94 a million BTUs. And we show here, if you are able to implement the Maryland Tier 1 REC values of 278 a million BTUs for the use of wood, you drive down the cost per unit of steam to $1.07 if you're not using flue gas condensation. But over to the far right, your energy unit cost for steam drops to 15 cents a million BTUs when you take advantage of that flue gas condensation and the improved efficiency of your system. Here's similar presentation using different technologies for your unit costs for cooling. Probably the most cost-effective, efficient systems out there that a lot of folks are familiar with are variable speed drive centrifugal electric driven chillers. And those are, you can see the cost of cooling per ton hour is about 5 cents. If we're looking at wood with a single effect chiller, it's a little over 5 cents, 5.8 cents a ton hour. Double effect chiller is a little bit less than that, 3 cents, a little over 3 cents a million BTUs, or excuse me, ton hours. But look what happens when we use that steam coming from the flue gas condensation unit and the heat you're harvesting there. It drives the cost of chilling down to wood-fired single effect chiller is less than a electric centrifugal chiller by about a little less than a penny. And with a double effect chiller, that cost goes down to 2 cents, a little over 2 cents a ton hour, a substantial change. And again, we show if Maryland Tier 1 RECs are able to be utilized, what the cost of chilling goes to here in Maryland when you're able to take advantage of that Tier 1 REC. Similar presentation for the unit cost of power. So that's the dollars per kilowatt hour. In Maryland, 14 cents a kilowatt hour off the grid. If we're using a back pressure steam turbine, $27 wood, $27 a ton wood, we can, using a back pressure steam turbine, generate that electricity for a little bit less, or a little bit, almost 2 cents a kilowatt hour. 1.5 cents if we use back pressure steam turbine with flue gas condensation. And again, we can lower the cost substantially using the REC value. You're getting electricity almost for free at a tenth of a cent with using wood, back pressure steam, and flue gas condensation.
Lou, we need to be mindful of time.
I think we have the same kind of approach for greenhouse gas emissions, for steam, for cooling, and for power. And kind of wrap this up with the opportunity here when you use wood, potentially use of wood in Maryland, is take a look at the opportunities and certainly make sure you address both emissions and the potential to use flue gas condensation. Thank you very much.
Thank you, Lou. Fascinating, interesting on the cost comparisons. Our next presenter this morning is Matt Hafner. Matt is the lead engineer, Chemical Unit Air Quality Permits Program with the Maryland Department of the Environment. He's been writing permits for the department since 2011 for a wide range of sources. He also manages the Title V Part 70 operating permits and assists other engineers with technical reviews of applications and permits. His Bachelor's of Science in Chemical Engineering and Master's degree in Civil and Environmental Engineering from the University of Maryland College Park makes him a Terp. His favorite tree is a black cherry. He has had 2 in his yard, which he says is good for birds, and since he's a birder, that makes it his favorite tree. Matt, welcome.
Hi, thank you. Let me get my screen shared up here.
I just want to remind while Matt's getting his screen together, and we'll be dealing with questions at the end of the program as time allows.
All right. So thank you guys. I will be talking about the air permitting requirements for Maryland Department of the Environment for installing one of these biomass fuel burning equipment. So I'm going to go over the regulations for biomass fuel burning equipment, and then I'll talk about what permitting forms are necessary, and then demonstrating compliance, basically, what the operator needs to know and needs to do once they install one of these units. All right, so Maryland has a definition of fuel burning equipment that is defined as boilers, internal combustion engines, turbines. And in 2014, they made specific biomass fuel burning regulations. They can be found in our COMAR 261109.12. And then you can read the biomass definition there regarding wood. So basically, wood residue, wood products. And so that's what, Dan Wilson was talking about that you would see with the wood chips and a lot of the standard equipment would use. And then there are also some federal regulations that I'll talk about too. The state regulations were based around some of the federal regulations, but there are also federal regs in addition to state regs. And I should clarify here that these regulations I'm going to talk about are for fuel burning equipment. We do have some wood dryers in the state, and they are regulated under a whole different set of regulations. So those do not apply here. This is just for, you know, energy and heat for fuel burning. So the main emission standards that we're looking at with biomass fuel burning equipment are particulate matter. And these are the regulations that you'll find in our COMAR 261109.12. And then, so I'm looking, you can see here at 30 and over over 10 to 30, it matches the NESHAP, the federal NESHAP in subpart 6J. What Maryland did was then create different standards for smaller units with stricter standards in the Baltimore, Washington metro region. And then just so you know, all fuel burning biomass fuel burning equipment is subject to the same NOx standard of 0.3 pounds per million BTU. And then fuel burning equipment over 30 million BTU per hour does have opacity standards in the New Source Performance Standard federal regulation. But I'm not gonna, you know, as Dan was showing earlier, a lot of these units are much smaller, closer to 10 or less. And that's what we've anticipated as coming into the state. So that's what I'm gonna focus on for the most part. But as you can see, these are the standards. They do drop. This 0.07, from what I understand from remembering the research that was done in 2014, would require a control device, like something like the electrostat precipitator that Lou was just mentioning. But just keep that in mind. All right, so permit applications. This is main thing you need to know is that first line there, a permit must be obtained prior to installation. Our permits are called permits to construct. And so that does mean it is a permit to construct the equipment. There are separate permits to operate, but they are often not necessary for this equipment. If you have a very large installation, you know, I mean, you're pushing 50 million BTU per hour, then you might require a permit to operate. You would require a permit to operate, but these smaller units would just need a permit to construct, which serves as your permit to operate as well, but you do need it before you install the equipment. So the main form is a Form 11, and I'll have links to our website where these forms can be found. But I did put down the key information that would need to be supplied with the form. Estimated annual fuel consumption, the stack information, general operating schedule, emissions estimates, and then workers' compensation insurance for the facility. That's a state requirement for all air permits, need evidence of workers' compensation insurance. And then you would need a Form 6 if a control device is used, which has more detailed stack information. So if the equipment does have an electrostat precipitator or a bag house or the multi-cyclone, a Form 6 would also be required. But if everything is just built into the unit, there's no control device put on, just a Form 11 would be necessary. All right, so demonstrating compliance. If you install one of these, the things you need to know is that there are tune-ups required every 2 years. That is in the state regulation as well as the federal NESHAP. And that is standard for all fuel burning equipment now with the federal NESHAP. It's not natural gas anyway. And there are a lot of companies that come in and perform the maintenance for the units. And then for boilers 10 million BTUs or greater, there will be an initial stack test and subsequent stack tests required to demonstrate compliance with that particulate matter standard. For boilers less than 10 million BTU per hour, we will accept compliance demonstrated through manufacturer's testing data. And that's basically, there's EPA protocol that basically says that this model unit has been tested and this is the emissions that we guarantee that it meets. And if that meets our standard, nothing else is required, you know, for demonstrating compliance with the particulate matter standard. Other requirements, this is basically standard with a lot of our permits. The minimized startup and shutdown periods, follow manufacturer's recommendations, that comes from the NESHAP, but is also in our regs. I already mentioned biennial tune-ups every 2 years. And then keeping records. Record keeping is our standard method of compliance for a lot of units that don't have you know, emission standards or don't do stack tests or things like that. And then the NESHAP does require notifications of compliance status and stack test. The compliance status is basically saying that you are doing your biennial tune-ups and operating, you know, within the manufacturer's recommendation for the unit. And if you do require a stack test, you know, saying that you have completed the necessary stack test. And then obviously notifications are required for any time there is a stack test. Our compliance program will come out and observe them. So I'm just about done here, a quick presentation. So here I put the links. You can find the permit to construct forms, as well as our state requirements and the federal NESHAP requirements. And because I believe we can get this presentation available, then you guys will have these links, help you find those. And there are instructions on our permit to construct forms, as well as contact information, which I will also be providing here. You can have my email there. I'm happy to answer any permitting questions that you have for biomass fuel burning or anything else for that matter. And I think that's all I had today.
Well done. I think it's important for our audience to see how much regulation applies to this energy technology and that Maryland is on top of it at MDE, particularly the idea that there's ongoing compliance in operations and maintenance as part of maintaining and keeping a system operating. So our next presenter is Kyla Cheynet. Kyla is the Sustainability Manager at Drax Biomass. Kyla was very PC in selecting her favorite tree as the white oak, which is the state tree of Maryland. She leads sustainability for Drax US operations, where she oversees program development, certification, and conservation initiatives for Drax Biomass pellet operations in the US Gulf South. Kyla also supports Drax's wider supply chain, working with pellet suppliers in the US and Canada to assure biomass sustainability requirements are met. She holds a master's in forest management and a bachelor's in wildlife management from Virginia Tech, which makes her a Hokie alum. She has been actively engaged in the forest industry across the southern US for over 20 years. And prior to joining Drax, she worked in forest management and sustainability for Mead West Vaco, Plum Creek, and Weyerhaeuser. Good morning, Kyla.
Sorry, I was on mute. Let's see if I can get this going. So actually, yeah, I realized I did not give you talking points for my white oak. And good morning, everyone. So that's probably because I like to talk about trees. So truthfully, I've just moved to Maryland and did not know it was a state tree. So I like it because it's a reliable source of hard mast for wildlife. It's also beautiful when it's grown on a good site in the forest, and also when it's grown in the open sunlight. It's fantastic for flooring and furniture, and it makes better supports for timber bridges than red oak does. So those are my reasonings. Now let's see if I can get my screen shared back. There we go. All right, so I thought I would start out by just telling you a little bit about Drax, and then I would move into sustainability challenges and how we approach them. So Drax is a renewable energy company based in the United Kingdom. We're best known for the power station that we operate near the town of Selby in North Yorkshire, England. Drax Power is the largest power station in the UK, connecting directly to the national grid. It supplies about 7 to 8% of the UK's electricity, or approximately enough to power 6 million homes. The power station has recently converted from coal to renewable biomass, making it the largest decarbonization project in the United Kingdom. We are also developing carbon capture and storage technology, which will allow us to remove more carbon from the atmosphere than is emitted, with a goal of becoming carbon negative by 2030. Over the last few years, Drax has also added some hydro stations to its portfolio, including one pumped hydro station in Western Scotland. In addition, Drax Group has a customer's business in the UK which sells renewable electricity to large businesses and industrial partners. And in the US, Drax owns and operates 3 pellet facilities, which ship about 1.3 million tons of pellets to the power station annually. The power station has chosen to use wood pellets as its primary energy source. Pellets have low moisture content and a high BTU value. They also work well with the existing coal-fired technology and are relatively easy to load onto container ships for transport. Drax biomass represents only about 20% of the pellets that Drax power station uses, with another 40 plus coming from other producers in the southern United States, and 17% coming from Canada, 17% from Europe, and less than 1% from one FSC certified supplier in southeastern Brazil. Drax pellet plants are located in Louisiana and Mississippi. These locations were chosen because of their strong fiber baskets and the recent loss of markets for low-grade fiber. And the other key component was access to deep water ports and rail transport. So we have a port facility in Baton Rouge that has the capacity to ship about 2 million metric tons of pellets a year. So that's about 40 vessels, container vessels. The pellets from Morehouse and LaSalle are railed to the port, and the pellets from Amit, which is only 57 miles away, are trucked. Because we own and operate our own pellet facilities, we're able to experience firsthand how sourcing interacts with our forests and our communities, which is extremely important to communicate to the UK and EU policymakers who ultimately decide whether bioenergy is viable and if it meets the strategy to meet current climate goals. So this leads me into our challenges that we face. So the biggest challenge is proving sustainability to UK regulators and a European audience who doesn't understand the scale of our southern forests or how we interact with them. So the UK just doesn't have the same resources as the US, and it's a struggle for them to understand the scale of the timber management harvest. So for example, the UK has only about 8 million acres of forest land, and the southern US has over 2 million. So it makes it a challenge for them to develop a legislative framework around sustainability. Our task is to evidence the controls that exist in the US and to communicate what we do so that beneficial sourcing of biomass is not unnecessarily limited. And Drax has taken a really proactive approach to this. We've recently updated our sourcing policy to incorporate recommendations made by the Forestry Commission's research agency. These recommendations define what good biomass sources are, and they go further than the UK regulations. So the second piece of our challenge is not different than the rest of the wood using industry, and that's just making sure that the sustainability controls that we have in place are working. But to meet both of the challenges, we're very fortunate here in the US to have an established wood supply chain, well-developed forest certification systems, and years of research and industry to back them up. The material we source is no different than what traditional wood-using industries like pulp and paper use. We use low-grade pine roundwood and forest residuals from thinnings and regeneration harvests. And regeneration harvest is a key, so we only take material from forests that we know are actively growing back. And I noticed that in Maryland, stumps is listed as a possible source of biomass, and that's something that is strictly prohibitive for us, so because that would indicate land clearing practices. So we are just working forests. We also use residuals from sawmills and other manufacturing facilities. And some of our suppliers have inwoods chippers, so they can use more tops and limbs. And inwoods chippers are usually paired with conventional roundwood systems, or they can be used to process the entire tree, which is really useful for first thinnings. And so here we have two photos of the same pine stand. On the left, you can see that it's closing out and there's a lot of hardwood competition. And on the right, you can see a section of the same stand that has just been thinned and processed with an inwoods chipper. So the inwoods chipping is really nice because it can take smaller material and allow us to get into the stands earlier to reduce that competition and increase productivity. Also lets light on the ground, which is really important for increasing forage for wildlife. So a little bit about how our sustainability program is structured. So as I said earlier, we have a wonderful mix of sustainability certifications to choose from here in the US. As we got started in this space, we were trying to figure out how to meet the UK regulatory requirements. They decided the best thing to do was to certify to all of them. So we are certified to 4 standard organizations: SFI, PEFC, FSC, and Sustainable Biomass Program. We hold chain of custody certifications with FSC, PEFC, and SFI, as well as SFI fiber sourcing and FSC controlled wood. The SBP standard was built specifically for the bioenergy sector, so it recognizes and builds on the other standards. And it also adds a GHG component necessary for regulatory reporting in the UK. Key components of these certifications are due diligence, risk assessments, track and trace, logger training, and landowner outreach. Conservation initiatives are also an expectation of several of our certifications, specifically SFI fiber sourcing and FSC controlled wood. But we're taking this to another level, and I'll explain that in just a minute. But first, I just wanted to walk you through some of our fiber sourcing controls. So we don't own any land. We don't purchase stumpage, which means we have to work with a set of trusted suppliers and collect as much information as possible during harvest setup. So we ask for information on harvest location, harvest type, forest type, species mix, and harvest unit size. And then we screen all of our harvests for high conservation values, or HCVs. So we've worked with NatureServe to produce a map of high-risk areas, which is available to the procurement team on an internal Google Maps platform. And before taking fiber from a tract, we plug in the coordinates into our Google Map rapid risk assessment layer. And if it hits one of our red zones, we do a deeper dive into our NatureServe data on ArcGIS. And if we identify anything, we can then work with our supplier and our landowners to make sure the HCV is protected. State wildlife agencies and natural heritage programs are partners in this effort. We also have a system to verify BMP implementation and HCV protection. Overall, we probably sample about 30% of our active harvests. And for our residual suppliers, we have contractual controls as well as a system of formal annual communication and audit. We focus on partnership and education when it comes to HCVs in the region. So circling back to conservation projects, as I mentioned before, Drax has been proactive in incorporating the latest recommendations from the UK Forest Research into a set of forest commitments. We've also partnered with a group called Earthworm, which is formerly known as the Forest Trust, to develop an approach for measuring and monitoring performance against these commitments. So we call this our Healthy Forest Landscapes Initiative. And we have 4 focus areas. We look at forest carbon, forest cover, biodiversity, and people. And we just kicked it off last year, and the pilot geography was our Amit biomass plant. We contracted with a number of different partners to develop methodology and remote sensing tools to look at biodiversity and forest cover and forest carbon. And then we also conducted a separate catchment area analysis and socioeconomic analysis using FIA data and other publicly available data, and as well as stakeholder surveys, so that we could really understand the forest and the forest we source from, the people who live there. So this methodology, it's been interesting to test it, but I think we have something that's workable, and we're starting to roll it out across our other geographies. So we have several. We're looking at some of our catchment area in the Virginia, North Carolina area, then down in Georgia, and actually out in British Columbia as well. And the goal of it is we hope to every 5 years revisit these areas and conduct the analysis again and look for changes. And so then we can, if we see a change, we can try to determine, is it positive or negative? And then is it at all related to our sourcing? So this is our effort to scientifically and transparently answer some of the questions about forest sourcing, and also to identify some conservation opportunities on the landscape. And to close out, I thought I would share just a few of our conservation efforts with you. So in the Morehouse sourcing area, we've partnered with the American Forest Foundation to improve forest stewardship and increase certification in northern Louisiana and southern Arkansas. This is a part of AFF's Southern Woods for At-Risk Wildlife Partnership, and it's funded partly by the National Fish and Wildlife Foundation. And it's a pretty exciting project. It's been going for 3 years, and we're really starting to see an uptick in forest certification in the area and just general awareness. So we're going to continue to fund that. We're also working on a pollinator project. And this was an effort that was initiated by our AMIT Mississippi procurement team as an effort to increase seeding and stabilization on logging jobs, and at the same time increase habitat for pollinators. So I have just dubbed it BMPs and bees. It's been a great effort. It's collaborative. It's been a challenge over the COVID times trying to get the seed we need. We're also working with the Pollinator Partnership, which is a NGO focused on protection and promotion of pollinators. And we hope to get seed on the ground this fall. And finally, we're working with the Longleaf Alliance and the Forest Stewards Guild to address conservation concerns related to native longleaf pine ecosystems and bottomland hardwood forests in the region. And our goal here is to enhance the understanding of these ecosystems and generate interest in their conservation and management. So we are planning to do this through a combination of methods. We'd like to do hands-on technical workshops and educational events. And we're also rolling out educational material to our residual suppliers as well. But we're really excited about our projects, hoping to build on them and continue to identify opportunities in our sourcing area. And that's really all I had. I know that was pretty quick. And it's quite different than the other presentations today. So, but it gives a different perspective, I hope, on it. And I think, you know, the context may be different, but use of this material, this low grade wood, is fantastic for the forest, and it's a good climate outcome. So I'm hoping that that Maryland will be successful in their efforts. And happy to take any questions.
Thank you, Kyla. We do have a number of questions that have been submitted on the chat. But before we do, we're going to do a quick poll of the audience again for those of you that are still on while we pull those up. If you can just take a quick minute to answer the poll question with hit your radio button, and we'll see how has today's program changed your perspective, if at all, on woody biomass energy and thermal energy solutions for Maryland. The questions that we have received from our audience will be addressed, if not in our time today, online and available on the website. Let's see what our answers are. Okay, so many of you have a broader perspective and some new ideas. about woody biomass energy. So thank you for participating in the poll. We have a few more minutes and we're going to run just a little past noon because we started a little bit late. But we have some questions that I wanted to ask the presenters. Dan, specifically, there's a question about what technologies have you seen to allow biomass boilers to condense flue gas for energy recovery and efficiency gains? If that's something that you could address really quickly.
Yeah, sure. So technologies are usually after the ESP or some other emissions control. We've got the particulates mostly out, and now you're creating a basically running through, I'll just call it a box that is, you run the flue gas into that box and they spray water in a counterflow to the flue gas. That cools it down, and there's a what I call a dirty loop of water that drops into a pan, basically rains in there, drops into a pan at the bottom, and that water is cycled back to the top or taken out of the system to be treated and sent to the sewer. And as it's doing that, it's running that dirty water loop through a heat exchanger to a closed loop that's the clean water, the heating system that you're trying to heat. And then after it leaves that, it's cooled down. It still has some moisture in it in terms of droplets, so you can remove that if you don't want to see that. But otherwise, you just send it out the stack. So that's generally how most of the technologies work, and there's a number of providers. A ton of the waste to energy projects and biomass projects in Europe use this at larger scale systems and in medium scale systems as well. So it's a very well proven technology that's pretty available. The thing we don't have in the US typically is the low temperature demand. So it's not really worth putting in if you don't have a use for the heat at 100, 140 degree water. Good uses for it are paper industry, heating processed water coming in, because it's coming in cold and then goes out pretty warm. You can pick up heat in that type of industry, or in buildings, domestic hot water for heating, things like that. So there's lots of opportunities, but they're somewhat limited in the US currently.
Thanks, Dan. Kyla, the question for you, is it possible for Drax to use hardwood biomass, or do you just use softwood?
Yeah, that's a good question. So yes, it is possible for us to use hardwood biomass, and we do. Drax does. Drax Biomass has chosen to use southern yellow pine basically because where we're located. We do take hardwood residuals, so we're getting some hardwood in the mix. But yes, it is possible.
Lou, there's a question about language that might Maryland's TREC regulation more advantageous adoption of thermal energy. Would states that you work with that we might look to?
I think New Hampshire and Massachusetts both have ongoing programs that could provide language. I think the biggest consideration in Maryland, and Dan can jump in on this answer as well, is just the clarity on can wood alone be used, or does it have to be mixed with other materials such as poultry litter?
Yeah, I think that's the biggest question if you read the regs or the rules. Is wood able to meet it on its own, not being mixed with poultry litter or animal manure?
In our analysis of those opportunities to use flue gas condensation or simply wood-fired energy for heating or cooling, we assumed in our analysis that wood on its own could be used in those systems.
Great, thank you. We have one comment that I want to share. One of our audience members asked, did Baltimore the Baltimore School project take into account the potential for a wood innovation grant? 250K, I think, is in parens, might be the ceiling on the grant, or the Community Wood Energy and Wood Innovation Grant, 1 million to 1.5 million. And we're not able to answer that because we don't know what the Baltimore School project developers considered, but it is worth noting for the audience that there are grants available through the Maryland Energy Administration for biomass energy solutions and technical support. Also, we'll be talking in our next program about financing the deployment of these systems, and Maryland Clean Energy Center can help with that. So I'm going to say that we've reached the end of our time today. We'd like to thank all of our guest speakers and webinar attendees for your participation. When you exit the webinar, Zoom will open a survey page in your browser. Please submit the form to ensure that we have your correct information for continuing education credit reporting and verification. If you need assistance, let us know at info@mdcleanenergy.org. We hope that you'll be able to join us for the final session, which is posted on your screen. All of our registered attendees will receive notification when the recordings for each session have been posted online at mdcleanenergy.org/biomass. The white paper produced as part of the Spurring Fossil-Free Biomass Initiative can be found on that website, along with the recordings from our earlier sessions in the series. Have a great day, and thanks for joining.